Hello everyone and welcome to today's webinar on the Master Series Modal Analysis and Floor Vibration features. My name is Michael Dowd, I'm the lead developer on the Dynamics add-on and I'll be presenting today's webinar. My colleague Dr. Martin O'Gara will be answering questions over the course of the webinar, so feel free to type in questions as I'm speaking. This slide here shows a general list of the features in the dynamic and seismic add-ons, with the things I'll be covering today highlighted in red and details of them shown in the grey boxes. First, I'm going to explain how to use Master Series to perform basic natural frequency and mode shape analysis. And this is the basis of all the dynamics in Master Series, and it is necessary before you can do any of the more advanced analyses. So our output from this will be mode shapes, natural frequencies, mass participation in any of the axes, and you can see your model stats as well. I'm then going to look at how you can use some of the time history analysis, particularly steady state and base acceleration, and some of the outputs available, for example, nodal displacements, member force snapshots, and node watches. And also I'm going to look at how we can import seismic accelerations into the base acceleration section. I'm finally going to have a detailed look at the new vibration design tools which we've been implementing over the last few months. So the first part of the dynamic module is the natural frequency analysis. The steps involved are as follows. One, we're going to need to check our model properties, which is over here. Because of the matrices used in the modal analysis, a lot more memory is required here than for your equivalent static analysis. And a rough estimation of this memory requirement is given here. When you've used software for a bit, you can use this value to give an indication of the amount of time the analysis might take. For reference sake, I'm running a Dell Precision T3600 with Intel Xeon quad-core 3.6 GHz processor. If the minimum memory required is up to 1 to 3 megabytes, the analysis will be pretty much instantaneous. 15 to 20 megabytes, it'll take a few seconds. The model here, which required 260 megabytes, took about 4 or 5 minutes to analyze. And a model requiring up to about a gigabyte of memory will take 40 or 45 minutes. So it's important to check this figure, especially if your model has any FE surfaces, which is now possible in the very latest patch, which we released last night. And because the degrees of freedom and the minimum memory, the amount of degrees of freedom and the minimum memory can get very large on models with FE meshes, and it could potentially take hours to analyze. So once we're happy with these settings, we move across to set up our model mass, which we do by clicking the Edit Mass Load Contribution. And this opens up a dialog that's similar to the way you edit the load combinations in MasterFrame. So what's actually happening here is we're using the load groups which we set up in MasterFrame and taking a factored amount of them into the dynamics as mass on the structure. Once you've set that up, you can move on and set up your analysis settings. So we've got, if your model is planar, you can do a two-dimensional analysis, and that will free up it'll take a lot less memory, take a lot less time to analyze. Once you can also choose to analyze a subset of the mode shapes for the first X amount, or mode shapes with natural frequencies between in a certain range. So once you have all this, you just press Analyze, and the output will be mode shapes. The output will be listed here. It'll be mode shapes, and their numbers here, their frequency, and the mass participation in any of the given axes. So let me just take you through a basic model of this, and we'll see just how very easy it is to do this and quick in Master Series. So what I've set up here is a model that could be an industrial tower frame, and the idea is that it's supporting 4 point loads up at the top here, and these are representing a machine which would be sitting up at the top of the tower. And the only other load on it is its self-weight, and that's all within the D1 load group. So we go into Dynamics. Another new feature, by the way, I should point out, is that we now use DirectX, the same rendering engine as we use in MasterFrame. So we get our nicely drawn models here in Dynamics now as well. And we check our model stats first. we see this model is going to take about 6.72 megabytes, which isn't very much at all, so we can afford to analyze all the mode shapes. We'll go to Edit Mass Load Contribution, and we've applied a factor of 1.5 to the D1 load group, which is the only load group with any loads in it. So we press OK there, and analyze all the natural frequencies. It's not 2D, so we can't do any of that. Just press Analyze. And we give this a couple of seconds to run. And you know the analysis is finished once this grid or list here is filled with values, and each of these rows represents a mode shape. So mode 0 at frequency 3.8 is shown here, and it's overlaid over the structure. You can adjust the scale here. If we turn 3D off, we can see it a bit more clearly, and we can play it and see how the mode is moving at that frequency. Another really useful feature is sorting the modes by their mass participation, particularly in the Y direction, because this is going to be critical for a machine vibrating up and down. So for example, we sort it based on the mass participation in the Y direction, and straight away we can see that the floor and the top level is vibrating at a frequency of 7.66 Hertz. And we can see it vibrating like that. So these are just the pure mode shapes. If we want to actually see how the structure, the floor in particular, or any is actually vibrating, we need to go and do a time history analysis. So I'm going to talk a little bit about how to do that now. So I'll jump back to PowerPoint. So I want to have a brief look at some of the things you can do after this initial modal analysis. One of these is the steady state analysis, and I'm going to use this to model a vibrating machine on the top floor of the tower we just saw. This tool allows the user to input a single or combination of sine waves that define a harmonic force applied to the structure. And then we can watch the steady state response to this force and use the output to design the members for the dynamic forces. So firstly, the user has to set up the harmonic force using this grid. So here's an example of a sine wave with frequency of 8 Hertz applied to these nodes, and if we show it in the Y direction, show this graph in the Y direction, we can see that sine wave. And it's important over here to set up your time history settings. Now these will be very much based on the frequency and the accuracy you want to achieve. The smaller the time step, the more accurate will be your time history analysis. And particularly relevant to steady state is the total time. Because steady state is showing us the response of the structure when it's reached a sort of cyclic, repetitive point in its deflections. Basically, we only need to do a total time that takes account of one complete cycle of these deflections, and then we'll be sure to have the worst case deflections and hence member forces. So we set up our total time step. The damping ratio is the damping within the structure. It's kind of an engineer's call based on the connections and the material type. And the magnification just has to do with the graphical display of your results, so it's nothing to do with the analysis. So don't worry about that too much. And then you run the analysis using this little obscure button here. And the output will be the maximum, minimum displacements in the structure, what time and where they occurred. The displacements and member forces at a particular, all over the structure for all the nodes in the structure at any particular time. And you can also set up node watches where you watch the displacement, velocity and acceleration of a node over the course of the analysis of any particular node. So I want to go into Master Series and show you how we can do this and then also use it in MasterFrame for design. So I'll open up Master Series now. So using the tower we just analyzed, we now have all these options available, whereas they were grayed out before we'd run the modal analysis. But we can click steady state now, and I've set up a harmonic frequency that runs at 50 Hertz, and it's applied to the 4 nodes upon which the machine is bearing down on the top floor. So this is kind of modeling a machine varying between plus and 3 kilonewtons and minus 3 kilonewtons at each of these nodes, and it's resting on top of the floor. And we can see this load by pressing the FY direction. We're going to analyze one complete cycle, and we can just press play now to see how the structure is going to behave under this harmonic load. And if you watch up here, we can see the maximum and minimum displacements in each direction are changing as the analysis is run. Our absolute minimum Y deflection is 0.047 of a millimeter, so that's very small, probably not worth any further investigation. But let's give this a shot. If the machine was, for example, vibrating at a frequency much closer to the natural frequency of the floor it's resting on, the deflections might be bigger. So let's try that out and just jump back to this tab here, check the natural frequency. We know the floor is going to vibrate about 7.66. So say your machine happened to have a frequency of 10 kilonewtons. Let's just see what happens then. I need to just change the total time and the time step here. And this time we're going to watch it over 2 cycles. And we will analyze that now and see what happens. Straight away you can actually see the floor vibrating in front of us here. It is magnified by 50, but we are reaching much higher deflections here in the y-axis of minus 2.22 millimeters at node 112 and at time 0.123. So I'll just show you the node watches here. I've set this up already, it's watching node 112 in the y-axis, and we're looking at displacement. We can see velocity and we can see its acceleration over the course of that analysis. We can also set up a snapshot, and this is probably the most important output feature here. We basically look back here and see the critical time 0.123. And we'll say, okay, let's see how the whole structure looks at that time. So put this in, add it to the list. So now we have that snapshot. No results yet because it needs to know this before the analysis is run, really. So we need to run the analysis again. And this time, at time 0.123, it's going to save a snapshot of the nodal displacements in the structure. And that's what we have here. And here are the member forces that are calculated from these. And the great thing is that we can send these back to MasterFrame and easily use them in MasterFrame for analysis and then design of members. So let's try and do that now. Exit dynamic analysis, say yes. Turn on DirectX here. Now I'm going to set up the load case that we're going to attach these loads to, and it's going to be set up so we can compare it to a load case, an identical load case without these dynamic loads. So I'm going to add a case, I'm going to copy load case 1, and then I'm going to paste it into load case 2. And this load case, both these now have just a factor of 1 on the D1 load group. So they're exactly the same. What I'll do is just rename the second one now, so for comparison's sake. And then what you do, you jump to special loads and dynamic snapshot, and we choose our second load case that we want to attach the snapshot to. And we go attach dynamic snapshot, pick the steady state snapshot we just created, and then it's got a load factor of 1. It's factored by 1, which is fine, and then we go analyze. And you can see the analysis dialog. It's showing us that a snapshot has been attached to this load case. So it's telling us to be prepared, and then we just analyze space frame. So it's analyzed now, view print graphical output. And I want to show you the deflected shape first. This is without any dynamic loads being considered, it's just under the self-weight of the structure. We can see the deflection of it. Now, we take the dynamic load caused by that machine, which, you know, it's caused the dynamic load at the worst time for that particular, for this structure that causes the worst displacement in the y direction. We now have a snapshot, and we've added this so we can see that straight away the floor is actually deflecting a lot more when the dynamic loads have been accounted for. And this deflection actually means, if we go to member diagrams and check out, for example, this beam here, we've got a bending moment of 4.61 kilonewton meters for this beam with no dynamic loads attached to it, to the load case. With dynamic loads, it's 7.4 kilonewton meters, so it's a very significant extra amount of bending moment in the beam, at that moment in time when the deflections were worst under that machine vibrating. So we think that this means, these extra forces, dynamic forces, can really be accounted for here. And now you can carry on with this and design this beam to this load case here, which has significantly higher bending moments than it did if they weren't accounted for. And before now, these may have been completely ignored or just accounted for in a kind of basic sort of way with a factor. And now we're actually getting the actual contribution that this dynamic load is making towards the bending moment in each beam. So I think that could be very useful to some people. So there's one more thing that I'd like to talk about here with this model. So I'm going to exit out of this. And that's another type of time history analysis back in the dynamics. And I want to look at the base acceleration tab. And I want to show you that the new features we've added in for importing seismic data, or any base acceleration data for that matter. Basically, until recently enough, the users would have been expected to import or input their data manually by hand into this grid here. And we realized that was kind of a ridiculous thing to expect the users to do, especially because most of the use of this would be for earthquakes where there's a lot of data. So it wasn't really feasible to input it by hand. So now we've given them the option of pasting it from Excel, or you can now import it, and you can import these 6 historical earthquakes. Their data is now shipped with Master Series, so you can import that data. And you can also import your own set of base accelerations if it's formatted the correct way and instructions are given on how to do that. But just for this demonstration, I'm just going to import the data from an earthquake that happened in Iran in 1978. So you can see when you press OK, the data is put into the grid, and there's like a lot of it here. 32 seconds worth of base accelerations at time intervals of 0.02 seconds. And we can flick between the different axes and see the forces or the accelerations happening in those directions. And I'll just turn this 3D off, and we can just watch this structure reacting to this earthquake. If I press play. Now it's done. It's gone through the 32 seconds there, and because we have a node watch set up, it's watched node 112 in the y-axis, and it's given us that node's displacement over the course of the analysis. We can zoom in and out on that, and also we can see the velocity and acceleration, and also at the bottom the root mean squared acceleration, velocity, and displacement there. So that can be useful for design. And as in the steady state, we can also output a snapshot of the structure at any particular time over the analysis to MasterFrame. We can use it for design and to take account of these dynamic loads in the design of our members. So that's what I wanted to show you there in terms of time history analysis. I'm going to jump back to PowerPoint now. And talk a little bit about the vibration design, which I'm sure is what most people are probably interested in. So here's the layout of the vibration design sort of tab. And there's a lot of options and settings here. It may look a bit intimidating, but I'm going to go through each one of them now, and hopefully it'll all become very clear at the end, and you'll see how easy it is to actually use this. So the first step here, and it's always going to be the first step, and it's the same with the response spectrum analysis actually, is that you add a vibration load case. And what each of these load cases is, and you can have more than one, is it's a placeholder for your settings and the options that you choose, and when you analyze, it does them all at the same time. You can kind of flick between the results and compare the settings, and how they compare to each other might determine which one you use for design, or which settings, or which code approach. So that's the first step, and then after that you move on to setting your options. So the first one you're approached with is the SCI P354 approach versus Concrete Society approach. And if you choose SCI, you need to determine a weighting factor based on where the vibrations and the response are. Like it has general areas, critical areas, or residential, and things like that. Then you've got your damping and your static force, the amount of force applied by the person or thing that's causing vibrations. And then over here you choose whether you want to do a steady state or transient analysis. If you choose steady state, you get the option of, you have to choose your Fourier series, and there's 5 Fourier series, I think, for the SCI approach, and 2 for the Concrete Society, although only one of them is really intended for design. It's their design Fourier series. And once you choose your Fourier series, you choose the frequency range over which you'll be testing the frequencies to determine the kind of critical frequency. And this depends on the Fourier series you use. For the walking, you want to test between 1.8 and 2.2. For staircase, it's 1.2 and 4.5. If you've got Concrete Society, they want frequencies between 1 and 2.8. And then down here you can actually look through your Fourier series values. And if you choose the final option that's available in both approaches, is to have a user-defined Fourier series, which is very handy because you can input your own ones and actually use Fourier series from one approach in the other, just for the ultimate comparing the two approaches. And if you choose user-defined one, you input your values down here, and this graph will update to display the Fourier series as you change the frequency or the values in your user-defined one, or the Fourier series itself. The next option is to use either single node or multiple node, and this is basically determines what sort of output you're going to get. I'll talk a bit about that in a second. And then after that, you also choose whether you want the response node, the node at which the response factor is being measured, to be the same node as the node that the vibration is applied to. I'll talk in detail about that and give an example on how to use that bit later. And then you choose your directions for the vibration and the response, and you choose the nodes themselves. And you can choose for the SCI approach the alignment of the person on the structure, whether they're kind of standing or lying down, and this affects how they perceive the vibrations. And also you've got the option to calculate vibration dose values, or include the resonant build-up factor, which can reduce the response factor. And if you know the path length, and the stride speed, so basically accounting for the fact that people aren't applying the vibration over that long a time. So often it's only a very short time that the vibration is being applied for, so you can reduce the response factor by taking account of that. And finally, you get the option to use all the modes that you've calculated in your natural frequency tab, or you use a selection of these modes, and the selection is often the most useful. And what I tend to do, as I've done earlier, is just use the first 10 or so modes in the y that have the most mass participation in the y direction. So then you run your analysis by clicking up here, and the output you get is, like I mentioned earlier, completely based on whether you've chosen multiple nodes or a single node. And if you've chosen our idea here is that people will probably work in such a way that they choose multiple nodes at first, and what this does is we'll look at nodes across an area, or it'll look at many nodes and determine their worst case RMS acceleration, response factors, and vibration dose values, and the worst case frequency of vibration for each node, and it'll show you the response factors and the worst case values for these for a group of nodes. And this can be used to identify critical areas in your structure, the areas that will have the worst response factors and that you need to pay special attention to. And once you know this, you can then go on and look at these the nodes with the worst response factors in your single node, with your single node output. And this will give you your RMS acceleration, response factors, and vibration dose values for the full range of frequencies across which you're testing. So You can use this to not only identify your critical frequency, but also kind of subcritical ones that are there's a bit of resonance happening, and you want to kind of just know at what input frequencies you need to be careful at and sort of keep an eye on. So that's how it all works. I'm going to go through a few examples now so we can see how it all was put into practice. So I'll jump back to Master Series. And I'm going to exit this and open up a nice staircase model. This is a model we got in from a user here. One thing that's maybe not immediately obvious is just how big it is. We've got it spanning in the x direction between 0 and 9 meters, so it's a long enough span. It rises from 0 to about 4 meters, so high enough rise as well. So you can see why you might be interested in seeing how this is going to dynamically behave. So we'll jump into dynamics now. And first thing we do, as always, is our modal analysis, and we check the minimum memory. It's a very small model, so we can afford to calculate all the modes. We'll edit the mass load contribution, just the D1 load group, factor of 1.4. So we're happy with that. That's just the density, the self-weight of the model, the structure. So analyze. Give it a couple of seconds, and we know now the analysis is complete because this list is filled. So our mode 0, we can click it, and we see that it's a fairly standard kind of up and down kind of mode shape there. So let's jump straight to the vibration design. First thing you notice is that all the options here are grayed out, and that's because we don't have any vibration design load cases, so the only thing we can click is actually to add a vibration design load case. So we'll go with SCI approach. We'll call it a general space. Damping of 5, static force 0.746 kilonewtons, just the weight of one person. We'll go with steady state, and we'll choose the staircase Fourier series. And in that case, we need to change the frequency range between 1.2 and 4.5. And we can look at the Fourier series here. There's only 2 harmonics in it. And we'll go with multiple nodes. So we've got our multiple nodes selected, and we'll choose to measure the response factors at the same nodes at which the vibration is applied. Select the whole structure, and the final thing is I only want to use a selection of modes to quicken up the analysis, so I'm going to go with the first 10 with mass in y direction. And then simply press vibration design. Straight away we see the model has been colored to show where the worst response factors are occurring, and that's a really helpful indicative tool here. So we can see the worst response factors are happening around here, and if we now look over at the grid, we can tell what that is. For each of the nodes that we've calculated a response factor is listed out here, and then the response factors themselves and the nodes are sorted into an a list that descends from the highest response factor. So we know our worst one is at the top here, and it's quite a high value, 99, and we can actually click that and it'll highlight it on the screen, and we know it's happening at 3.477 at node 89. So that's useful, and we can now actually go and look in a bit more detail if we want. We can say, let's look at node 89 and how it's actually performing over this frequency range by clicking single node here. Type in 89 and vibration design. So here we get our classic response factor graph here with one big peak here, and the response factor, it's 99 at 3.48 Hertz. So that's how we determine the response factor for that node. And that's staircase. I want to show you another model now. And this model is going to include a finite element mesh, which is brand new as of yesterday. We can now do finite element meshes in the dynamics. So we just go to open, and we'll open this big floor. So that's the mesh there. I should point out that you don't want to have too dense a mesh, because the amount of degrees of freedom as the mesh gets denser becomes very, very high, and it makes it tedious and very slow to dynamically analyze. So it's quite a loose mesh. And if I turn 3D on, we can see the slab here. And if we look a bit closer, we can actually see that it's using another new feature, which is these offset beams that are offset from the center line of the slab. And this is quite a new feature. And you can see graphically the slab is resting on top of the beams, but also analytically that's taken account of, and the beams are attached at the top, at their top surface all along the slab. So we think this will make the dynamic analysis in particular extremely realistic for these kind of floors. And we'll get much more realistic mode shapes and sort of vibrations. So we'll just go to dynamics. And just give it a second or two to come in, because I'm loading it off the network. It takes a couple more seconds. You can see here this list is full. I've already analyzed this because it's quite a 305 megabytes. Took about 5 minutes, 6 minutes. Don't want to be sitting here in the webinar doing that. So we can actually look at our mode shapes here. If I turn 3D off, you can see the first few are actually lateral mode shapes, and these have the slab moving kind of horizontally as opposed to vertically. And the first vertical ones here, mode 3, got a nice little peak there. And if we sort by the y direction mass participation, we can see that mode 14 has the most mass moving in the y direction. So that's quite a... These ones will be the important ones when we come to vibration design, all the ones that have mass moving in the vertical direction. So that's where we'll go now. And again, first thing I'll do is just add a load case, and I'm happy with SCI approach so far. We'll go with residential non-critical area and keep it at walking. This frequency range is suitable. Just a quick scroll through our harmonic series there. And in this model here, I want to discuss a bit more in a bit more detail the difference between using the response node, this checkbox here, response node equals dynamically loaded node. So when I have this checked, essentially what the software is doing is it's going to go through each node that I select. So I'll select every node. And for each of these, it'll go through and apply a vibration at that node and then measure the response factor that vibration causes. So I'll just show you how that will look now after I tell it which modes to use. And everything else is set up, so I'll just press vibration design. And so what this basically means is that very quickly we can determine critical areas in our structure, and it's generally relatively safe to assume that the worst response factor at the critical areas will be caused by vibration at that area. So it's a fast bit of a shortcut to determining the critical areas, I suppose. But if we uncheck it, this allows us to do something else which is a bit different. Basically, we can determine an area over which to measure the response factors, but the response factors caused by vibration in a different area. So say we have an operating theatre that takes up a certain amount of space, but the people within it aren't moving around that much or causing that much vibration, but they're extremely sensitive to vibrations caused by people walking in a corridor adjacent to the operating theatre. Then we might be interested in the response factor caused by that sort of movement, and that's very easy to set up here, and it's just as simple as selecting your two areas and then analyzing. So that's what I'll do now. So I'll select my response area first and say our operating theatre takes up this amount of space, and then say we have a corridor running alongside it just here. Actually, I should clear that list first. And just showing a mode shape there for a bit of a grid effect. So we have a corridor here, and then I just press analyze. And one thing you'll notice is this analysis takes a good bit longer than the previous ones. For each node here in our response factor area, it's checking the response factor caused by vibrations at each of the nodes in the vibration area. And for each of those nodes, it's also cycling through the entire frequency range, so 100 different frequencies. And from all that, it's determining the worst case response factor in our response factor area. So we can see that straight away. It's still the same node. It's node 684 here, and a response factor of 3.14, basically in the center of the room. But interestingly now, we know that it's not being caused by vibration at that node. So what node is causing that response factor? You can just click it here. We know that vibration at this node is now causing the worst response factor in our operating theater. So we think this tool could be very powerful and be used to, if you know that maybe your response factors are turning out a bit too big for your whole floor, but you know that vibrations will only be being caused in the corridors, for example. You might be able to use this tool to reasonably reduce your response factors, and also it's just fun to play with, so I'll leave that one there. And I want to talk about one more thing, which gives me a good excuse to open up another cool response factor model. So this model here there's 3 staircases, and then also interestingly it has a finite element landing here, which also uses our sort of offset beams, so you can see the beams are just nicely sitting under the finite element deck there. So let's jump into dynamics again. And again, I've pre-analyzed this because it just would have taken a bit too long for the webinar, so we can look at our mode shapes in the Y direction, make sure everything's alright, and jump straight to the vibration. Now what I want to do here is discuss the differences between the SCI P354 and the Concrete Society approaches. So I'm going to add 2 load cases this time, and set up each one for the SCI and one for the ConcSoc. So for the SCI I'll choose a general space, and I'll choose the staircase Fourier series, again between 1.2 and 4.5. I'm going to use the same response as dynamically loaded node and select the entire structure. And again, as per usual, take the first 10 modes with mass participation in the Y direction. So we have 3, 5. And that is the SCI approach setup. Let's move to our second load case. So let's reset everything here because it's a fresh load case. Let's change to Concrete Society, and we're going to use the design Fourier series. So you can see straight away the Concrete Society doesn't give you half as many Fourier series options, it just has one really for design. And they say specifically at the start that this Fourier series and this approach that they're promoting can be used on any structure on which humans walk, so they recommend this for even staircases, I'm sure. And one thing to note is that their Fourier series is designed to be used between frequencies of 1 and 2.8, so compared to the SCI staircase, which was 1.2 and 4.5, this is a lot, I think, a bit more realistic, to be honest, because it'd be very difficult, I think, to apply a frequency of 4.5 hertz vibration to a staircase by just walking or moving on it. But for the sake of comparison, I'm actually going to use the same frequency range here, so I'm going to go between 1.2 and 4.5. And choose multiple nodes, select the entire structure again, and then selection of modes, that selection. And now I believe we're set up now for a direct comparison between these two. So jump back to this, and let's look at the SCI results first. So looking at it top down, you can see our critical area is this staircase here, and if we click it, we can see it's actually node 109 at a frequency of 4.071 Hz. So this is giving a fairly high response factor of 39.305. and that wouldn't be acceptable in a lot of design criteria. So how does the concrete society approach compare? Well, it's the same distribution of response factors, very, very similar. The most critical node is again 109, it's just happening there. But here we've got a response factor of 16.18, and that is acceptable in a lot of design criteria. I believe, up to about 20 might be fairly standard for staircases. So, why is one approach giving such a significantly lower response factor? I want to talk about this. And the next step in that, or the next phase in sort of investigating this, would be to look at node 109 in a bit more detail. So that's what we'll do for both of these. We'll just look at 109 between the frequencies 1.2 and 4.5. It's as simple as just going single node and typing in 109. And do the same over here on 109. And now we just analyze. And straight away we're getting our little response factor graph here, and this is a very classical looking one. I think it's nice. We're seeing our little peaks, and these are happening at sort of resonant frequencies, and then we get our one big response factor up here, 16.18 at 4.07. So that's a nicely shaped graph. If we look at this SCI approach, it's absent the peaks, and we get our one big response factor, 39.31. So I'm going to just move back to PowerPoint now to compare these two and talk about why they're so different. So here are the two graphs. The figures are actually slightly different here. It's the exact same model and the same analysis. I've just used different load factor while calculating the mode shapes. So you get 31 in the SCI for the response factor and 12.69 in the concrete society. And there are basically two differences between these graphs, and they're both caused by the Fourier series that the two different approaches use. The first difference is that we get these nice little peaks here in the concrete society, and we don't get them in SCI approach. This is basically happening because there are more harmonics used in the concrete society Fourier series, which is shown here. So you see we have 4 harmonics versus the 2 that the SCI P354 staircase approach uses. And this allows more interaction between the Fourier series and the mode shapes that we use to calculate the response factors, and hence we get these nice little peaks, and we don't get them over here. Now, the second and more important difference is that the response factor is just way bigger over here, more than twice as big as it is over here. And the reason for this is that the Fourier coefficients used in the SCI approach, even though there's less harmonics, the sum of these is actually still more than twice as big as the sum of all the Fourier coefficients used over here. For example, with frequency of 2, doesn't actually make a difference to the Fourier coefficients in the SCI. We get a sum of 1.32. But if we put 2 in here, we're getting a sum of 0.582. So you can see straight away that there is a valid reason why the SCI P354 is actually more than twice as big. And I believe that the concrete society approach seems a bit less conservative for staircases, but it may be more realistic, especially in terms of it's acknowledging that you're not necessarily going up to 4.5 hertz frequency, which, interestingly, if we just jump back to the master series really quickly, even in the SCI approach, if you were to only go up to a frequency of even up to 3.77 hertz here, the response factor is still quite reasonable. It's still under that 20 mark. So, if at more realistic frequencies down here, you're getting a very reasonable response factor. So, finally, I'd just like to thank everyone for their attention, and I would like to just quickly reiterate on some of the key points. The Dynamics module is an add-on to MasterFrame, and some of its most useful features would include the Modal Analysis, in which you determine your natural frequencies and mode shapes, and the ability to perform a dynamic analysis, a range of dynamic analyses and time history analyses, and determine the forces in your model due to dynamic forces. So you could use this for blast and impact loading, dynamic wind loading, like with the Tacoma Narrows Bridge, and moving loads and vibrating machinery, as I showed you before. And with all of these, you can have your node watch set up, see how the node's moving over time, but more importantly, you can output the member forces in your structure at any given time during this analysis back to MasterFrame and use it in MasterBeam to design your members and design them so that they account for these extra dynamic loads that would otherwise possibly get overlooked. And also, our vibration design package, which we've been slowly adding to over the past few months, it's reaching a point of basically completion. At this point, it's allowing us to look at our root mean squared acceleration, our response factors, vibration dose values over a range of frequencies. It also allows us to look at, just that one node, or to identify critical areas and the critical input frequencies for these areas or for particular nodes. We can do either of the analyses. We can do the analyses with the SCI, P354, or the Concrete Society, and do transient or steady state analysis. And we can use the Fourier series from either of these approaches, or define our own Fourier series. And finally, we can also choose to use just a range of the modes or a selection of mode shapes. This really could reduce the analysis time, especially for the separate areas analysis here, where we have our vibration occurring in a different area to our response factor, which can sometimes take quite a while. I also look very briefly at importing seismic base accelerations, and this feature is part of the seismic add-on, which needs to be purchased in addition to the dynamic add-on, but it's very cheap, so everyone should buy it. And as well as what I showed you, the seismic add-on would allow users to analyze their structure using the lateral force methods, which is a kind of static approximation of seismic forces, or the response spectrum method, which uses the mode shapes to kind of arrive at a good approximation of seismic forces, or the complete base acceleration time history analysis, which is what we looked at just there. And using that, you can then, as per the steady state, output your member forces at critical times during that time history back to MasterFrame, analyze them there, and then design for them in MasterBeam. Okay, and that's the end of the webinar. I'd like to thank you all for listening, and goodbye.